Behind me is a target drone from World War II dubbed the OQ-2A. This vehicle represents the Army Air Force's first widespread use of uncrewed, remotely piloted vehicles. What's important here is that it highlights two of the Air Force's objectives in the development of autonomous collaborative platforms, along with an early example of foundational technology. These two objectives are cost and lowering risk for aircrew. The traditional approach to train anti-aircraft gunners during World War II involved towing a target sleeve behind a crewed aircraft. OQ-2As, however, were much less expensive to build and operate. Moreover, they eliminated the danger to target tow aircraft pilots from any misdirected anti-aircraft fire. A key autonomous collaborative platform technology area represented here is human-machine interfaces, or HMI, which facilitates control and communication with an uncrewed vehicle. The original HMI system for these OQ-2A radio-controlled drones employed a telephone dial, imagine an old rotary telephone, with each number representing a command to the vehicle. This clunky HMI system was replaced with a much more effective and responsive joystick control box. Today, effective and considerably more complex HMI technology remains a foundational element in creating and advancing autonomous collaborative platforms.
Hey guys, Dougie Fearless here. Real quick, please take a moment to subscribe to my channel. I'll see you again at the end of this video. Thanks guys.
This B-17 behind me, the famous Memphis Belle, represents some of the challenges that modern autonomous collaborative platforms, or ACP, are solving for our nation today. Those challenges include cost, the ability to produce at scale, and operating in highly contested airspaces. Now, this B-17 Flying Fortress, along with the B-24 Liberator bomber, were used in our strategic bombing campaign against Germany in World War II. Bomber air crews operated in highly contested airspace, which led to over 8,000 B-17s and B-24s lost in combat, and more than 30,000 heavy bomber crewmen killed in action during that campaign. Because these bombers were produced in such large numbers, however, the U.S. Army Air Forces were able to sustain such grievous losses. That said, these heavy losses at times force leaders to pause campaigns or avoid important targets in order to protect the force structure. In addition to protecting the lives of our airmen by taking them out of the cockpit, ACPs are also addressing the challenges of cost and the Air Force's ability to quickly produce aircraft in large numbers. As our airframes have become more and more sophisticated, they take longer to develop, cost more, and are produced in smaller numbers. This poses a real problem for our warfighters, but ACP promise a solution to meet these needs at cost and in numbers like during World War II. Behind me is a G3 target glider, which has a fascinating connection with today's collaborative combat aircraft and autonomous collaborative platforms as programs developed within our labs. Developed by the McCook Field Engineering Section, a predecessor lab organization, the G3 was an early, unpiloted, and unpowered air vehicle employed by the Army Air Service in the 1920s as a cost-effective means to train both aircraft gunners and fighter pilots. It was used to train fighter pilots by setting the controls to fly randomly after its release from a carrier aircraft. What's interesting here is that fighter pilot training was also the intended role for the uncrewed Fury vehicle born from AFRL's Adversary Air Bandit program. The Fury design was in turn selected by the Air Force Life Cycle Management Center for its Collaborative Combat Aircraft Acquisition Program and is now designated the YFQ-44A. So, this very distant cousin from a century ago has a remarkable connection to the collaborative combat aircraft being acquired and developed today. This X-29 research vehicle behind me illustrates two foundational technology areas that enable autonomous collaborative platforms, or ACP. The Air Force Research Laboratory's predecessor labs worked on fly-by-wire technologies in the 1960s and 70s, leading to the first production combat aircraft to use fly-by-wire, the F-16. Fly-by-wire works by taking the control inputs from the pilot, sending them to a computer, which makes the appropriate adjustments, and then sends signals to actuate the control surfaces. This approach helps allow very unstable aircraft like the X-29 to be able to fly. The second technology is composite structures. The X-29's forward-swept wings generated powerful torsional or twisting forces, and so it needed a very strong but light structure. This problem was solved through the use of composite materials. From these early beginnings, the labs have continued to advance fly-by-wire and composite structure technologies, and which today's autonomous collaborative platforms now employ. Behind me is the QU-22B, which was fielded in the Pave Eagle program during the Southeast Asia War, which is also known as the Vietnam War. The QU-22B aimed to resolve some of the same issues that ACP, or Autonomous Collaborative Platforms, are solving today. The QU-22B was created to operate in contested airspace as part of a program called Igloo White, where the Air Force dropped sensors along the Ho Chi Minh Trail. These sensors would pick up enemy activity and then broadcast them to an orbiting EC-121R, a vulnerable four-engine aircraft with a large crew, which then sent the signals on to a ground surveillance center. The uncrewed QU-22B was intended to replace the EC-121R, thereby saving costs and eliminating danger to air crews. In the end, the QU-22B had some problems with reliability stemming from it weighing more than anticipated. Thus, it only flew as a two-person crewed vehicle during combat operations in Southeast Asia. Flashing forward to the modern day, AFRL's further development of autonomous collaborative platforms is solving some of the same problems that the QU-22B tried to solve during the Southeast Asia War.
Hey guys, Dougie Fearless here. Real quick, please take a moment to subscribe to my channel. I'll see you again at the end of this video. Thanks guys.
AFRL's development of uncrewed vehicle autonomy and other related technologies reaches back more than 2 decades. A significant early milestone was the X-45, where AFRL partnered with DARPA and NASA in an advanced technology demonstration from 1998 to 2006. The X-45 was an autonomy-enabled platform that tested the ability for these types of vehicles to conduct suppression of enemy air defenses, or SEAD. In 2005, a test saw 2 X-45s autonomously react to a pop-up simulated surface-to-air missile site and, with remote operator approval, conduct a successful autonomous attack on it. There were 64 test flights between 2002 and 2005 in this program, but unfortunately it was canceled in 2006 as this capability was not required for ongoing operations in Southwest Asia. In 2014, Dr. Dave Walker, Deputy Assistant Secretary of the Air Force for Science, Technology, and Engineering, recognized the increasing problem with combat aircraft costs, acquisition timelines, and other challenges facing warfighters. He looked to AFRL to solve these problems with a direction to go build something. This resulted in the establishment of AFRL's low-cost attritable aircraft technology program, which looked at how to design and build uncrewed vehicles at cost and in numbers. The early part of the LCAAT program involved extensive analysis of design, cost, operations, and manufacturing factors. AFRL scientists and engineers worked with several aircraft manufacturers to explore opportunities to achieve high performance while keeping unit costs for uncrewed aircraft low. Technologies from the low-cost attritable aircraft technology program ultimately fed into AFRL programs developing autonomous collaborative platforms, or ACP. LCAAT also birthed the XQ-58A Valkyrie under the low-cost attritable strike demonstration program, which proved that it was possible to create a high-performance, uncrewed vehicle for under $3 million. Moreover, the Valkyrie became a key platform in autonomy tests and development for both the Air Force and the Marine Corps. About 50 years ago, in the 1970s, there were groundbreaking demonstrations of armed, remotely piloted vehicles and maneuvering remotely piloted vehicles using the Ryan Firebee platform. The BGM-34 successfully deployed several types of ordnance, with the idea being to develop it into a multi-mission strike modular design that could be used for reconnaissance, strike, or electronic warfare missions. And in fact, this idea was employed to create the XQ-67 in AFRL's low-cost attritable aircraft platform sharing program, or LCAAPs. The XQ-67A's basic chassis was then employed in the YFQ-42A, which was then selected for the Air Force Life Cycle Management Center's Collaborative Combat Aircraft Program of Record. There were also experiments done with a maneuvering Firebee that could pull up to 6 Gs, and it was dubbed the XQM-103. In spite of some amazing results from these demonstrations, this effort was canceled in the late 1970s, and we would have to wait some decades before we saw armed, uncrewed vehicles again. The first aircraft chosen by the Air Force Life Cycle Management Center for its Collaborative Combat Aircraft Acquisition Program were two vehicles that traced their roots to AFRL aerospace vehicle development programs. The first vehicle was the XQ-67A, which was part of the low-cost attritable aircraft platform sharing program, or LCAAPs. And the idea behind LCAAPs is the same kind of thinking that automobile manufacturers use, where they may have a common chassis, drivetrain, and engine, which are then used to build pickup trucks, sedans, and SUVs, thereby reducing cost and maintaining supply chains for production. The XQ-67A was designed and built with the same type of philosophy, and it first flew in February of 2024. The Air Force Life Cycle Management Center selected two designs for the initial cadre of the Collaborative Combat Aircraft Acquisition Program. General Atomics' entry, now designated the YFQ-42A, uses the same LCAAPs chassis as the XQ-67, thus putting this modular approach into action. The second vehicle chosen was the Anduril Industries Fury, and the initial design for this came from AFRL's Bandit program, which involved AFWorks and the Aerospace Systems Directorate. The need behind the Bandit program was to create an uncrewed adversary air vehicle to help train fighter pilots, and the YFQ-44A shares basic shaping and configuration with the Fury designed for Bandit, but scaled up in a few key areas to better fit mission needs. And so the first two collaborative combat aircraft ordered by the Air Force came directly out of AFRL programs, and they represent only the first line of vehicles and the start of what is to come for the future of flight.
Hey guys, Dougie Fearless here. Real quick, please take a moment to subscribe to my channel. I'll see you again at the end of this video. Thanks guys.
This F-105 Thunder Chief, better known as the Thud, and its air crews represents some of the issues and challenges that modern autonomous collaborative platforms are looking to solve. The F-105 was our primary bomber aircraft in the Rolling Thunder strategic bombing campaign over North Vietnam during the Southeast Asia War, better known as the Vietnam War. The skies above Hanoi and Haiphong were heavily contested, and the North Vietnamese had an integrated air defense system that included radar-directed anti-aircraft guns, surface-to-air missiles, and MiG interceptors. Not surprisingly, operating in these dangerous skies caused heavy losses, and more than 300 of these F-105s, nearly half of their production run, were lost during the conflict, and worse still, with the loss of many of their air crews. This problem was exacerbated by the fact that the F-105 was out of production, so each one lost could not be replaced. So, once they were gone for good. The high production rates and relatively low cost of uncrewed autonomous collaborative platforms offer a modern solution to solve this past Department of the Air Force problem. The Air Force Research Laboratory, or AFRL, played a unique and foundational role in developing autonomous collaborative platforms, or ACP, and by extension, Collaborative Combat Aircraft, or CCA. AFRL played this essential role in two major ways. One, building and providing the technology and facilities that help develop and enable it, and two, providing the leadership required to bring all this technology together and take it across the finish line. AFRL advanced numerous technologies from the 1990s to today that were required to be able to create ACP and develop their robust ecosystem. The many technologies included autonomy of various types, such as flight autonomy and mission autonomy, rapid manufacturing, low-cost airframes, human-machine interfaces, human-machine teaming, collision avoidance technologies, communications and sensors, just to name a few. Moreover, AFRL brought down risk that outside partners either would not or could not take. AFRL leadership also played a major factor in being able to create ACP by partnering and guiding industry, engaging with warfighters, collaborating with acquirers, and working with other outside partners. All of these efforts together permitted AFRL to create and transition this revolutionary new capability known as autonomous collaborative platforms.
Hey guys, Dougie Fearless here. I'm a United States Navy submarine veteran, and I really appreciate your support. If you enjoyed this content, please consider subscribing to my channel. As always, if you're a veteran, I want to thank you for your service and your sacrifice. I will see you guys again very soon. Dougie Fearless,